Finally, another exception to the octet rule can be observed when dealing with atoms beyond period 2, because these atoms may have what are known as expanded octets. Okay, in other words, they can accommodate more than 8 electrons around them. These atoms are said to be hypervalent. Okay, so third row and below and beyond, you can have expanded octets. And the reason for that is their outermost shell is a third shell. They have 3s, 3p, and 3d subshells, so they can accommodate more electrons. The outermost shell is much larger, and they can accommodate more because they have more. You have an additional subshell there, the 3d subshell. Whereas atoms in the second period of the periodic table, the outermost shell is the second shell, and for n equals 2, you can only have 2s and 2p subshells. So the most you can put in a 2s is 2 electrons. The most you can put in a 2p subshell is 6 electrons. So you're limited to 8. Okay, so the most you can, so the second period atoms, okay, cannot exceed more than 8 electrons around them. So let's just do a quick check, see if you got that one. Which atom cannot have more than an octet? Carbon or silicon? Here's carbon, and here's silicon. Well, carbon is in the second row, right? So the electron configuration of carbon is helium core, 2s2, 2p2, and the most it can accommodate is 4 more electrons around it. So you cannot have more than an octet for carbon. Silicon, on the other hand, is in the third row. So the outermost configuration, the outermost shell of silicon can accommodate more electrons because of the 3d subshell. So which of these atoms must have an octet when sharing electrons with other atoms? Okay, nitrogen, boron, phosphorus, or none of these? The answer, none of these. Okay, that's the problem right there. It's not and the octet rule is not a requirement. In fact, we've seen boron as an exception. We've seen nitrogen with an exception. Okay, phosphorus can have an expanded octet. They don't have to have an octet. No atom has to have an octet. So that's just our way of trying to get a very good first guess as to what the structure would be, is to assign octets to atoms. They don't have to have an octet. Okay. In fact, hydrogen can't have an octet because it can only have a duet at the most, because hydrogen only has room for 2 electrons in its outermost shell. How about this question right here? Which atoms can have more than an octet of valence electrons when it shares electrons with other atoms? Sulfur, nitrogen, okay, carbon is right here, or hydrogen. Well, if you want more than an octet, you have to go beyond row number 2. So row number 1, the most you can have is 2 electrons. So hydrogen has to have a duet, max. Carbon and nitrogen, the maximum they can have around them would be 8 electrons. They cannot exceed the octet. Okay, and then sulfur right here is the correct answer. It can have an expanded octet. So let's take a look at structure that might require us to draw an expanded octet, or something that might suggest that an expanded octet would be better. And in the case of sulfate ion, this is certainly the case because that allows us to avoid a large formal charge. Sulfate ion, if you recall, is SO4 with a -2 charge. So let's figure out the Lewis structure for this. Sulfur contributes 6. Okay, a free sulfur atom has 6 valence electron. Oxygen, just call them 6A, also 6 valence electrons. There are 4 oxygens here. So, and then the -2 charge means you have 2 more electrons. So 6 plus 24, that's 30. So you have a total plus 2, you have 32 total electrons. So what you do here is you surround your sulfur by oxygen. Okay, and then you assign an octet to each of the oxygen atoms. So this oxygen up here has already one bonding pair, so it needs 3 more lone pairs to get an octet. Same thing for the oxygen on the left. The oxygen at the bottom also needs 3 lone pairs. The oxygen on the right needs 3 lone pairs to get an octet. Let's see how many we have so far. So we have an octet around this oxygen, an octet around this oxygen, an octet around this oxygen, an octet around this oxygen. That's 4 octets. So that's 32. That accounts for all 32. So let me redraw these. I'm just going to say sulfur with 4 SO bonds, and each oxygen has 3 lone pairs on it. And square brackets, we put a -2 charge on the outside. Well, that looks good. You have an octet around each atom, okay? But let's see what the formal charges are. Okay, the formal charge on the sulfur. Let's look at the sulfur. A free sulfur atom, we say, has 6 valence electrons. How many electrons, valence electrons, does it appear to own here? The sulfur atom here has 1, 2, 3, 4 bonding pairs. So half of 4 bonding pairs would be 4 electrons. So 6 minus 4, this sulfur has a +2 formal charge. That's not good. Okay, so how can we lower the formal charge? How can we lower a positive charge? We push electrons towards sulfur. The way you push electrons towards sulfur is to move these lone pairs. Okay, let me clean this up a little bit. Okay, sulfur. You can imagine moving one of these lone pairs over here to form a double bond. Okay, that would give a sulfur an extra electron because half of that pair will now belong to sulfur. That brings it down, so it will now appear to have 5. 6 minus 5 is +1. In fact, you can move another one there. That would give sulfur another electron that it will appear to own. So 6 minus 6, that would give you a 0 formal charge. So you can get a 0 formal charge on the sulfur if you put 2 of those lone pairs to make double bonds between the sulfur and the oxygen. So the structure that looks like this, so now I only have 2 lone pairs on this oxygen, double bond between this sulfur and the oxygen with only 2 lone pairs, and then this oxygen still has 3 lone pairs, and this oxygen still has 3 lone pairs. We'll have a 0 formal charge on the sulfur with a -2 charge. Okay, of course, this is one of many possible resonance structures. Okay, so it's like you have basically partial. These bonds you would expect that these bonds to be not quite single bonds, not quite double bonds, but sort of like halfway, 1.5 bonds. Okay, so the resonance hybrid you might draw as something that looks like this. Okay. So you notice in this particular case, sulfur has 4 plus 4 plus 2 plus 2. That means it has 12 valence electrons around it. So it has more than an octet. It has 12. Okay. Formal charge, okay, would be 0 because a free sulfur atom would have 6, and here it owns half of these 6 pairs, so it appears to own 6. 6 minus 6 is 0.